Hey, welcome everybody to our next series of our Excel Tech Talks. I'm super excited to introduce to you Johannes from Somag. He's going to explain us a lot about our mounts. So for achieving highest quality aerial imagery, obviously having a stabilized mount in place is a huge advantage. Would you just frame for us a little what the mount actually does during the collection?
Basically, the mount compensates for the movement of the aircraft. So it compensates for roll, pitch, and yaw, those three axes, to make sure that the sensor stays aligned to collect all the quality data that it needs to collect.
In recent talks that I had with people, and there is actually very often this, maybe you can call it kind of a misconception, that the mount is actually a motion compensation device, especially for the angular movements. Can you maybe elaborate that a little?
It can compensate for the most of the motion, for sure, but there are limits as well. The critical point is during the exposure of the camera, and all those small movements that come from the aircraft, they need to be compensated for sure, but it's not possible to be reduced into nothing. Yeah.
So yeah, that very well aligns with what we have found out when we developed our adaptive motion compensation, that we really need to take care, especially of the small remaining angular motions that are still in the imagery. So can you tell us maybe a little bit about limits and correlations that are happening in the mount while it's working?
Yeah. You've got physical limitations for sure, how fast the mount can provide the movement to compensate for the movement of the aircraft. Also, you've got the inertia of the camera because of the higher payload of the sensor. Vibrations, for sure. They can be compensated, especially with our isolation ring, for sure. But in general, there are some small movements in the end we cannot compensate at all.
I noticed that you guys actually also developed a very interesting feature to compensate the forward motion component. Would you care to explain that a little for us?
So this is our overlaid rotation correction feature. And what we basically do is we put on top of the stabilization of the platform some sinus movement or in pitch. So it can compensate for this forward motion. And our goal with the GSM 5000 is to be able to get an exposure time from 1/500 of a second up to 1/250 of a second. So that's our main goal, yeah.
We are standing here in front of your newest baby, the GSM 5000. It would be amazing if you maybe lead us through the highlights of your new product.
Yeah, for sure. We try to get all the input from our customers in the development of the GSM 5000. So we made sure to increase the movement range. So we get up to 10.1 degrees in roll, 8.1 in pitch. And also we increased the rotation of the yaw axis up to 177.5 in both directions, so almost 360 degrees. We also tried to reduce the interface to a minimum with this touch encoder here, and also made sure we've got a smooth surface with no high points on something. We turned the whole hydraulic system upside down to lower the pivot point down to 20 millimeters above the base plate. So the rotation of the sensor is reduced during the compensation, during the mount. And also we've got less vignetting. And so,
yeah. So the camera just sits lower.
Yeah.
Is that also helping for larger payloads if it sits lower? So if they're heavier, does that also contribute?
Yeah, for sure. Yeah.
Okay, awesome.
To get the center of gravity even lower to the mount. Yeah.
Even the GSM 4000 was good looking, but I must admit that this one here really took it to the next level.
Thank you.
That's really awesome. So if you're using a mount, you install it in a plane. Obviously, those, let's say, installation circumstances can be very different from each other, right? So you can maybe have more space available, less space available. And also, maybe you can talk a little bit about kind of a best practice approach, how to install it properly, what to watch out for.
Make sure that the sensor and the camera, the sensor and the mount doesn't collide with anything in the hedge or in the aircraft itself, for sure. Else you need to limit the movement range of the mount to make sure nothing gets hit. Also to reduce the angle of attack, you can use some wedge underneath the mount to be able to get the whole movement range of the mount during the flight, for sure.
Okay.
And something we always see is that the pilot is still in the turn when getting to the next line, and the first picture or data collection is during this turn, and the mount just goes in the end stops, and that's not a good thing. Yeah.
Maybe let's talk stick with the wedge idea just for another second. Can you maybe just talk a little about the correlations between the compensations that you're having, right? Because if you want to compensate the angle of attack, so angle of attack basically means when the plane is flying straight, the wings are not straight in relation to the airstream, right? So there's a certain angle that's called what we call the angle of attack in aviation, right?
The roll and pitch angles, they are linked to each other. So if you fly with, let's say, 4 degrees in pitch, you limit roll for sure. So when using a wedge, you get the mount back, and you've got the whole range of movement for the compensation for the aircraft movement. Yeah.
Okay, so we're just creating a better starting environment where we can really make the most out of the compensation that the mount can produce without any limits. Yeah.
Correct.
Awesome. Yeah. Johannes, it was a pleasure to have you here, talking a little bit about mounts, misconceptions, relations in compensation, and all the good stuff. So thank you for being with us.
Thank you for having me.
Our pleasure. I hope you enjoyed this Tech Talk, and see you in the next video.